Right, Thursday weekend. Still got more than 0 people in the theatre. It's remarkable. Okay, so I guess yesterday's lecture prompted another 60 people to do the quiz, but still, there's plenty more of you who must be saving it for tomorrow when it's due. Well, assignment 3, I'll have to sort out question 7 and 8 tonight and keep marking assignment 1 and assignment 2. So today we'll continue on with functional dependencies and normalisation, and maybe get on to relational algebra, and then final 2 topics next week on week 10, and then we'll talk about the exam. And I've got no nerd today. Oh, you meant to go? Oh, doesn't matter. Alright, so where were we up to? That's right. Okay, so we were working out keys, given a set of functional dependencies. What's the key for the table? So once again, you can see we've got these random collections of letters separated by arrows. Looks a little bit weird in this context, but basically what's meant to happen in real life is that you take real attributes and you work out how these attributes are related, and that's where these functional dependencies come from. A lot of the time when we're playing around just demonstrating how decomposition and so on works, we just give these one-letter attribute names. So imagine that we've got, I think this might be, yeah, beauty. So I looked at those first 3 yesterday. Let's have a look at the 4th one. Alright, so remember that we can work out what set of attributes forms a key for a relation by taking the set of attributes, computing its closure, and if the closure includes all of the attributes, then the original set of attributes is a key. And how do we compute the closure? Well, we keep repeatedly applying those functional dependencies, so that you're kind of treating them like rewrite rules. So if I have, right, so I'll start out with BGH, and I can apply this rewrite rule because I have B, G and H. Could I apply any other rewrite rules? Not at this stage. So I can apply that rule and add E to my set of attributes that can be derived starting from B, G and H. Once I've got E, I can then apply this rule to add F to my set, and once I've got F and B and G and H, what else can I apply? Where'd that come from? How do I get A here? A determines D. Oh, how interesting. Alright, so I've got to this point here, B, E, F, G, H. What rules can I apply from here? Ah, of course, the one I didn't see. F determines A, therefore I can add A to my set, so I end up with this. Once I've got this set of attributes, I can pick out some subset of those attributes that happens to be the left-hand side of a functional dependency, like these ones here, and then I can add all of the attributes on the right-hand side into my gradually growing closure. So that'll give me that. And once I've got C included, I can add E, which I already had. And what else can I add? Oh, because I've got A, I can add D. So that gives me the entire set of attributes, and therefore BGH is a key. I've posed the question, are there other keys? I'll let you work that out. And there probably are. And in general, all of these algorithms, or all of these methods, are generally non-deterministic, so there are typically multiple solutions. So finding a key, this is one key. I'm sure if you take a different set of starting attributes, you might end up also producing this, which means that the new set of starting attributes that you chose is also a key. Alright, here's another one. Right, so a very simple one. We've only got two functional dependencies. I can't take any individual attribute and derive all the others. If I start from A, well, I got nothing, because the only way I can do a derivation from here is to have A and B. If I start from B, once again, same problem. The only place with B on the left-hand side also requires me to have A in the set. So, and C, right, well, C will allow me to derive B, but there's no way I can then get A. So it looks pretty much like A is going to have to be part of any key. And so if I take AB, then I can apply that directly, and that gives me all of the attributes, therefore AB is a key. If I take A and C, well, I've got A, I've also got C, so therefore I can apply that, and I end up with ABC. And so AC is also a key. Is there any other combination? No, there can't be. So it has to involve A before it can be a key. And I guess I should have mentioned that, if you take the set of all the attributes that are mentioned here, that's the set of attributes that are involved in this relation. Alright, so here's another one. So clearly this has got M, N, P, Q, R as the attributes. So eventually, if I'm going to find a key, the attribute closure from that key has to be M, N, P, Q, R. So if I start with M and N, that allows me to derive P. Once I've got P, I've got N and P. So that allows me to derive Q. Once I've got Q, I can derive R. Therefore, Mn by itself is a key. And one final one, ABH. Well, it's pretty obvious that I can apply this first functional dependency to get C. Once I've got C, well, I've got A already, so I can apply this functional dependency to add D and E to the set. Once I've got that far, what do I do? Which one? I should have written down which functional dependency I was applying. A, B, C, D, E, H. So I need to find a functional dependency that I haven't already used, which has got some combination of these on the left-hand side. D, E, where am I getting G? I've got B and H, okay, so I can apply this rewrite rule, if you like, to add G to the set. It also adds E, but E was already there, so that's harmless. And once I've got that, I can continue the derivation to end up with this. Therefore, the closure of A, B, and H, the attribute closure of A, B, and H, is a set of all attributes, so A, B, H is a key. So what do you say? Well, it's useful to be able to work out what might be a key for a table if you didn't already know. But if you did know something about the interrelationship of the various attributes, you could work it out. Alright, well that's all very nice playing games with symbols. Let's play some more games with symbols, but these games are a little bit more useful. So normalisation allows us to get insights into the amount of redundancy in tables, and also the notion of normalisation basically involves taking a schema which has some redundancy and rearranging that schema to reduce the amount of redundancy. And if we're lucky, we can rearrange it in such a way that we've eliminated redundancy entirely. So, first thing that normalisation gives us is the ability to say how much redundancy is in this schema. And the second thing that it gives us is a bunch of algorithms that allow us to transform the schema into something which is less redundant. And of course, to do this, once again, we're drawing on functional dependencies, so that's why they're important. Right, so they talk about 6 different normal forms, and who knows, someone might have come up with another one in the last few years. First, second, third normal form. Sort of low-level structural things. There's a definition of what they are on the next slide. Boyce-Codd normal form. Similarly, that's kind of similar to third normal form, and then we've got fourth and fifth normal form, which we don't normally worry about, but they exist. And if your schema is in fifth normal form, then you're guaranteed that a lot of redundancy problems have potentially gone away. So if something's in fifth normal form, it's guaranteed to be in fourth normal form, or BCNF, or third normal form, or second normal form, or first normal form. So saying that a schema belongs to a particular normal form tells us about the level of redundancy. So if a schema is simply in first normal form, then potentially it's full of redundancy. If it's in second normal form, it's got less. If it's in third normal form, it's got even less. If it's in BCNF, it's got even less redundancy, although these two things are kind of similar, and so on and so on. So normally we only worry about these. First normal form is a really weak statement about the structure of the data. And basically all it says is that all of your attributes have atomic values. So that's kind of the way we think about that anyway. So we assume this is part of the relational model. So every relational schema that we come up with is already in first normal form. In second normal form, now we start to worry about functional dependency, and we want to make sure that any non-key attributes that appear in the table depend on the key. So we haven't got stuff floating around in the table that's kind of not related to the key. That having something in second normal form gets rid of a certain amount of redundancy. And having things in third normal form and BCNF basically means that there are no attributes in the table that don't depend on key attributes that aren't in the key. So everything in a particular table depends on the key. And so if you've got something in 3NF or BCNF, then you've basically eliminated redundancy. So the process of normalisation is one that tries to put a given schema into a particular normal form. Now obviously the first thing you do, you check, is the schema already in that normal form? Yep, I'm done. I don't have to do anything. But in fact, the very first thing you do is decide what normal form you're interested in. So typically, as I said, we choose BCNF or 3NF. So here we're talking about putting a schema into a particular normal form. What that means is looking at each of the relations in that schema and checking whether each of them is in a particular normal form. So we check each relation. If we discover a relation that's not in the normal form we want, then we have to restructure that, and the standard way of restructuring is to partition it into subrelations, which we'd also call decomposition. So we start with a particular relation that's not in the normal form we want, we break it in two, and each of those subrelations that we've created is hopefully closer to the normal form we want. And if we do the partitioning in a certain way, different for each of the normal forms, then we guarantee that we're moving closer and closer towards the whole schema being in the particular normal form we want. So we simply repeat that partitioning until all of the tables that we've got in the schema are in the right normal form. So we might have started with 3 tables and we end up with 6 tables in the schema, but the original 3 tables weren't in, let's say, third normal form, each of the 6 tables that we've produced is in third normal form. So therefore, the whole scheme is in third normal form, and hopefully, well, guaranteed we've eliminated some redundancy from the system. Okay, so the difference between BCNF and third normal form is that BCNF does get rid, if you've got a schema in BCNF, it's not going to have any redundancy due to functional dependencies. Fourth and fifth normal form have redundancies sort of across tables. So here we're just interested in dependencies within a table. So we've got rid of all the redundancy coming about from that. However, the way BCNF partitions things is that some of the functional dependencies might be lost in the partitioning. Now, in the decomposition. Right, third normal form gets rid of most redundancy, not guaranteed to get rid of all of it. However, one thing it does do, it preserves all of the functional dependencies. Now let's quickly talk about what happens with decomposition. I just want to show a quick example. So we've got a table ABC, and amongst the functional dependencies related to that table, we happen to have this one here. So clearly AB is a key for this table. And if this was the case, we wouldn't be decomposing it. But let's say that we did. We split this table into 2 tables, S and T, where table S has just A, B, C, table T has just A, B, and D. Now this particular functional dependency isn't relevant to either of these tables because neither of the tables has all of the attributes mentioned in the functional dependency. Okay, so a functional dependency is only relevant to a table if all of the attributes in the functional dependency appear in the table. So if we still wanted this functional dependency to be in the system somewhere, or to apply to the relevant tables, what we could do, remembering that AB determines CD, we saw yesterday that we can rewrite that using Armstrong's rules into AB determines C and AB determines D. So if we take those 2 functional dependencies, this does apply to this table because all of the attributes mentioned are there, and this dependency applies to this table because all of the attributes mentioned in the functional dependency are in the table. Now, of course, all of the attributes in the functional dependency doesn't have to cover all of the attributes in the table. We might just have some of the attributes involved in a particular functional dependency. So that's how functional dependencies can change as you decompose things. In this case, we haven't actually lost anything because if we take the set of functional dependencies over the whole schema at the end, then we can reconstruct this one because we've still got these 2 floating around. Okay, so you've got the notion of dependencies applying to a table and dependencies across the entire schema, which is all of the dependencies on all of the tables. Right, so that's the difference between BCNF and 3NF. BCNF, you might lose some of the dependencies entirely, which may or may not be a problem. In third normal form, you guarantee that all of the functional dependencies in the original system will still apply to the restructured system, but you haven't necessarily eliminated all of the redundancy. Okay, so standard transformation to move towards a better normal form is to decompose a relation into sub-relations. So you take a relation R and split it into relations S and T. Now you can't just arbitrarily say, right, I've got a table with A, B, C, D, E, F. I'm going to make a table with A, B, C and another table with D, E, F. Part of the deal is that you want to be able to reconstruct the original table from the transformed relations. And so, one thing we have to have effectively foreign keys linking the two tables together. So if we did have A, B, C, D, E, F, we could have A, B, C and C, D, E, F. So we've got a link between the two tables, which is going to allow us to put the two tables back together and reconstruct the original table if we want to. So the properties of decomposition are that the set of attributes has to cover the entire set of attributes from the original table, so we can't throw attributes away altogether. But of course we can have attributes appearing in both tables, and the unit is all right, as long as we cover the entire set of attributes from the original table. We can't have no common attributes across S and T, because otherwise we can't put them back together to reconstruct R. And definitely what we want is to be able to reconstruct R. So we can put S and T together as a join operation, and we want to be able to achieve R, given that. So, as I said, you can't do an arbitrary decomposition. You can't go A, B, C, D, E, F. How do you do the decomposition? Well, the normalisation algorithms have rules that tell you what kind of decompositions are allowed. So effectively what normalisation is all about, it's taking the schema and to some extent redesigning the schema so that it has better properties than the original schema. So let's have a look at this example here. It's kind of like that bank example we had before, but it's basically talking about loans. So you can see that we've got, a standard problem of having information about branches stored in two places. I should have included assets there. So if we do updates, then we have to make sure that we update all of the tuples that reference the downtown branch. So this has got redundancy, and we want to try and get rid of that by doing some kind of decomposition. Alright, so let's have a look at a possibility. The first one is what I said was no good earlier. So this is like typing A, B, C, D, E, F. If you do that, you've effectively lost some information. So doing this by taking the branch name, branch city and assets, all the branch information is one table, in one table. And you might say that sounds like a good thing because it will get rid of those update problems if each branch is represented exactly once in the branch table, but putting all of the custom loan information in a separate table, we've lost the connection of which branch a loan is held at, for example. Alright, so that information, that decomposition doesn't work. What about this decomposition? So here you can see that we've kept a link. So the customer name appears in both tables. So in theory we can do a join, branch customer and customer loan, put them together, and hopefully we'll be able to reconstruct the original table. So that's what the branch customer table looks like. You can derive that directly from the previous slide. Actually, one thing I should check. 1, 2, 3, 4, 5, 6, 7. Yep. 2, 3, 4, 6, 7. Right, so it has the same number of tuples as the original table. If in doing this decomposition, we ended up with some tuples that were identical. So imagine that we just took branch name and branch city, we'd end up having downtown Brooklyn. Now remember that this whole relational model, it's all set based, so you'd end up with having a single entry for downtown Brooklyn if you did the decomposition like that. Here though, we've got all of those tuples were distinct, and even when you effectively project on the first 4 attributes, they're still distinct. So we end up with that, and hopefully I didn't mess this up. Yep. So also we've got 7 tuples here, basically just taking the last 3 columns of the original bank loans table. Alright, so there's a decomposition which allows us to put the decomposed tables back together to hopefully reconstruct the original table, but it doesn't work. We can reconstruct all the tuples of the original table, but the way things are going to work out when we do a join is that we end up with extra tuples. So we've got that tuple there that didn't exist in the original table. It's a byproduct of what's happening with the join. You can go back and have a look at those 2 tables just to see how we've ended up getting this one. Similarly, all these blue tuples are ones that weren't in the original table, and they're basically a byproduct of a particular customer having multiple loans, and the fact that the customer loans table and the customer name allows us to join with the customer name in the original table ends up producing extra tuples. Okay, that's clearly not what we want. The original description of what I said we wanted was that if we take the 2 subtables and join them, we should end up with the original table. Right, so we've ended up with something that's too big, and despite the fact that we've got bigger, we say that that is a lossy decomposition because we've kind of lost some critical information. The fact that this particular customer had a single loan with this branch. So if we've got a good decomposition, then yes, we should be able to reconstruct the original table. And if we can, if that's the property of the decomposition, then we say that's a lossless join decomposition. Alright, so how do we define all these normal forms? Well, here's a description for Boyce Codd normal form. So a relation schema is in BCNF if okay, so here we're talking about a particular relation, so we look at all of the functional dependencies for that relation, and either the functional dependency is trivial, so x determines x, or xy determines x, something like that, or the left-hand side is a key for the table. And I said superkey, you can add extraneous attributes if you want, but basically what we're really interested in here is that the left-hand side of all of the functional dependencies related to that table should contain a key. So that's for one relation, and we say that the overall schema is in BCNF if all of the relations are in BCNF. Now, a couple of things that we can see from, or that you can derive pretty easily from this, is if you've got a relation that just has 2 attributes, it's going to have a functional dependency that says either A determines B or B determines A. Whichever one is on the left-hand side is the key, and therefore the whole key determines the rest of the attributes. So any 2 attribute relation is in BCNF. So if we've got a relation with a particular key and some other attributes and the rest of the attributes in that table, then basically we should have a functional dependency on the table that says the key determines everything else. Now that may be split across a number of different functional dependencies. So let's imagine the key is AB and the other attributes are C and D. So we could have a single functional dependency that says AB determines CD, or we could have AB determines C, AB determines D. Either way, in both of those functional dependencies, the thing on the left-hand side is the key for that table. Alright, so if we take a schema and we transform it into BCNF, we're going to get rid of all of the updated anomalies that I mentioned before, which crop up with redundancy. And also, we guarantee that when we put the tables back together, we're going to get the original table. However, one thing we're not guaranteed is that all of the functional dependencies that we had in the original system still exist in the final system. How might that happen? Well, basically, there might be a functional dependency on A, B, and C, D, and there might be a functional dependency A determines C, another one B determines D, which apply to the original table, but no, that's not the example I wanted. Maybe my original one was right. So we might end up with AB determines C, AB determines D, and none of the tables in our final decomposition have all of A, B, and D in them. So we might end up with a table that just has B and D. So that FD, AB determines D, no longer exists in the final schema. I need to think of a good example for where this is the case. So remember that functional dependencies tell you something about the semantics of the underlying problem domain. So you may lose some of that information. You haven't lost anything about the data, but you've simply lost the fact that maybe there's some connection between these two attributes. So if it's critical that you preserve all the FDs from the original schema, don't use BCNF, use 3NF. There's an example down there. Cool. Alright. So let's have a look at the BCNF algorithm. So we start with a schema, which is a set of relations and a set of functional dependencies. What we get at the end is another set of functional dependencies, which should be closely related to the original set. And we also get out a new schema where all of the relations in the new schema are in BCNF. So how do we do it? So we've got a set of relations, and let's say for the sake of argument we start out with a single relation. So we're kind of like that bank loan schema where we've got everything stuffed into one table. Clearly we need to break it up, but in any case we've got our bank loan table. So we look at the bank loan table and pretty soon we're going to discover it's not in BCNF. So what we do is we pick any one of the functional dependencies that breaks BC, or that violates the BCNF definition from a couple of slides ago. So we can choose any functional dependency that causes a problem, if you like. As soon as you say something like this, choose any of the possible ones, you end up with talking about a non-deterministic algorithm, so there's not a single solution. So if you choose this functional dependency, you might end up with this set of tables. If you choose this functional dependency as being the problem, you might end up with a different set of tables. Either way, the set of tables that you end up with, if you apply this algorithm, is guaranteed to be in BCNF. Alright, so we found a functional dependency that looks like this, and that causes BCNF to be violated. Alright, so what do? Basically, we take that table, S, and split it. So we remove S from the original set of tables, so that's what that's talking about. And then we create a new table that doesn't have any of the attributes from the right-hand side in that table. And we also create another table that simply has the attributes from the functional dependency in it. Okay, so we started out with a table S. We've ended up with two tables, one of which based on this functional dependency. One of the tables has had the attributes from the left-hand side, the right-hand side of the functional dependency removed, and the other new table that we're adding into the system has just the attributes from that functional dependency involved. All right, why does that get us towards B, C, and F? Well, if this functional dependency on S caused a problem, if we get rid of all the attributes on the right-hand side, that problem goes away in what's left of S. And if we create a table that's just got the attributes from X and Y, then it's likely that this functional dependency isn't necessarily going to cause any B, C, and F problems down the track. So, at each iteration of this algorithm, pick one of the tables and look for functional dependencies that violate B, C, and F. Based on that functional dependency, decompose that table into these two things. Remove the original S table from the overall database schema and put these two tables in its place. So essentially what that's saying. Right, so let's try applying that to the bank loan schema. So if we thought about it a little bit, it'd be pretty easy to come up with a couple of functional dependencies. Branch name determines the asset, so if you know which branch you're talking about, that determines what the asset's value is. It also determines where the branch is located. Similarly with a loan number, that determines the size of, if you know what the loan is, then you've got the information about how big it is, and you've also got the information about where it's held. So those two functional dependencies are there. So if we take these two things and take the original bank loans table and try to work out what the key is, well, it can't be just these two because they don't include the customer name. So if we take the branch name and we take the loan number and we take the customer, that gives us a key for this original table. Alright, so as soon as we've got that, we've got a key and we've got a big table that contains all of these attributes, and straight away we can see that it's not in B, C, and F because either of those functional dependencies doesn't satisfy the B, C, and F requirement. That essentially what the requirement is that for any functional dependency, the left-hand side is a key of the table. So this is only part of the key. So what we need to do, we decompose and we create a table based on those attributes, which is, which is that one there, and we create another table which is the original table without these two attributes. So that gives us that table there. And I've made up some sensible names for those tables, for the new tables. So the bank loans table no longer exists. What we now have in the schema, in the database schema, are those two tables. Alright, so let's have a look. If we look at the branch table, well, you can see that what we did with that decomposition was we effectively created a table that would satisfy that functional dependency. And in this table, that's the key, and therefore that whole table is going to be in B, C, and F. Now, of course, if there was some other weird thing like branch city determines assets, then it still wouldn't be in BCNF, and we'd have to do some more decomposition. But the way it stands, it's definitely in BCNF. Oh yeah, alright, so just to note, once I've got this relation schema, I know that its key is branch name because there's only one applicable functional dependency, this one here, and that tells me the branch name is the key. Similarly for loan info. Alright, so if we look at speaking of loan info, have a look at loan info. There's only one functional dependency relevant to it, and that doesn't contain the entire key, I hope, on the left-hand side. Okay, so the key for that loan info table are these two attributes. This functional dependency doesn't have customer name in it. Therefore, we've got a dependency that doesn't depend on the whole key. Therefore, we violate BCNF. All right. So once again, how do we fix this? We decompose and we create a table based on that functional dependency, which is that one there. And we create another table which comes from the original loan info table, but has those attributes removed, so that's what we end up with. Alright, if we look at these two tables, alright, I should have worked out what the key was. In fact, there's no functional dependency that's relevant for that table, so it's kind of in BCNF by default. You can't find a functional dependency that violates BCNF for this table, and in any case it's a two attribute table. And for the loan table, well, it was based on this particular functional dependency, which means loan number is the key, and that's the only functional dependency relevant to the table. Therefore, it must also be in BCNF. So now we've got three tables. We've got our branch table, we've got our loan table, and we've got our borrower table, all of which are in BCNF. Therefore, the whole schema is in BCNF. Right, so here's something, yeah, we can probably do this before the break. Okay, so now we're not looking at real attribute names and real functional dependencies. We're just looking at some that we've been given. Okay, so we've got a single table with all of the attributes in. These are the functional dependencies, and if we looked hard enough, we could work out, this might have been one of the examples we had before. We know that that's a key. Alright, well, one problem straight away, I mean, we could look at any of these functional dependencies apart from this one, and they would violate BCNF. So, arbitrarily choose one, choose this one. Doesn't have the whole key on the left-hand side. In fact, it has none of the key on the left-hand side. So we can do the decomposition step. So create a table with A, D, and E, and remove D and E from the original table. So we'd end up with those two tables. And all right, so what are the applicable functional dependencies? I think the only one is that one there, because none of the other functional dependencies just have A, D, and E. What happens if we break a few up? That's not going to help us. Alright, so that's the only relevant functional dependency. A is therefore the key, therefore the only functional dependency has the key on the left-hand side, therefore R02 must be in B, C and F. Oh yeah, we see that there. Alright, so what about R01? So clearly, since it doesn't have D and E in it, this functional dependency is no longer relevant to this table. So these are the ones that continue to be relevant. And once again, what we've got to do here is we've got to work out what the key is for the new table. It's not necessarily the same as the key for the original large table. So it's determined by the set of functional dependencies that are relevant to this table. And if we play around a bit, we can end up with B and H being a minimal key, if you like. So starting from B and H, we can derive G, then we've got B, G, H, we can derive F. Once we've got F, we can derive A and H, and I think that gives us everything. So, that's the key. Alright. So if we look at this particular functional dependency, it doesn't have the whole key on the left-hand side. Once again, the attributes on the left-hand side are not related to the key at all. So we do the decomposition step again. We make a table just with the attributes from the functional dependency, and then we get rid of the attributes on the right-hand side from the original table, giving us that. Okay, so now we've got these two tables, and we have to look at them again to make sure that they're in B, C and F or not. Alright, so if we look at this one, I don't think we can find any functional dependencies. You know, in theory we could split this one up and say F determines A, F determines H, but neither of those attributes, apart from F, happens to be there. I can't see any, so we don't have H in this table, so that functional dependency doesn't apply either. Right, so basically there are no functional dependencies on this table, so therefore we can't find a counterexample that violates B, C and F, so we say it's in B, C and F. Right, if we look at this table, AFH, we can find one functional dependency, and in fact it's the one that was used to produce that table, and we've already seen that if you've got a dependency like that, that tends to give you the key, and therefore the table is in B, C and F. So that's in B, C and F. So that table is in B, C and F. And what else have we got? R02 is in B, C and F. So the final schema involves tables R02, R03 and R04. All of those tables are in B, C and F, therefore the whole schema is in B, C and F. Now, you know, these kind of examples are a bit less satisfying because it's basically meaningless symbol manipulation, but certainly a slightly simpler way of showing how these algorithms work. As soon as you have realistic attribute names, all of the functional dependencies tend to be quite large and difficult to deal with. Alright, so that's an example of using the B, C and F decomposition algorithm to produce three tables, each of which is in B, C and F, therefore making the entire schema in B, C and F. So this was the original schema, was just a single table R that had all of the attributes in it and all of these functional dependencies. Alright. Actually, if we wanted to, we could probably look through here and find out which functional dependencies no longer existed in the system. I'll leave that as an exercise. Alright, so let's have a break there, and then we can have a look at a slightly more realistic example of decomposition and see what it gives us.